All right, why don't we go get started? So welcome back everybody to EE290C. So just a couple of administrative things. As a few of you already noticed, I posted the homework last night. So that's going to be due basically a week from yesterday, so like Wednesday 5 p.m. It shouldn't be too long, but having said that, don't delay getting started on it because it'll just really make sure you actually understand things. And I will actually be posting the first phase of the project fairly shortly. So you'll also want to get going on that because that'll be due also fairly soon. That first phase will, let's say, look more like a homework, so to speak. But still, you should really definitely get going on that because, as I said in the beginning of the semester, the project is going to be quite substantial. So you'll want to just make sure you're on top of things there because otherwise you'll have a big pile of things at the end of the semester that'll be very tough to actually complete. Okay, I think that's, the only other logistical thing, I think I've basically gotten it from most people, but if there's anybody that didn't send me an email with sort of which project group that they're going to be in, please go ahead and do that just so that I've got the information. I think I got it from everybody, but just in case, please do send that over. So any questions on anything before we sort of dive back in, or? Okay, so last time we were sort of finishing up talking about essentially equalizer circuit design, and we finally got into DFEs, and we talked a bit about sort of what sort of sets the limitations in terms of building DFE summers, and then we finally just started getting into talking about basically one of the trickiest things to do in the DFE is usually close that very first half, simply because it has to deal with essentially the small analog signal at the input of the comparator, regenerate it up to full rail, feed that back, and then resettle it all sort of within a bit time or so. So we talked about sort of a few techniques to try and speed things up. We talked about splitting the summation between a couple of nodes, but we also mentioned that that has a couple of limitations. We then also talked about, just really quickly, sort of just trying to push it by doing, let's say, clever circuit design, which usually involves just doing sort of all current mode logic kinds of things, so making even the comparator become CML. Of course, eventually you'll probably want to get this back to CMOS, but nonetheless, you can actually push on things fairly well. Maybe up into this about 20 gigabits per second or so in kind of 65 nanometer technology. But the last thing we ended up on was saying that, if you really want to push it, and if you don't want to have to sort of move all the way into the CML, or in fact even beyond certain data rates, even in CML, you might have to do this. There's this basic idea of essentially trying to not really close the loop, but instead doing what's called a loop unrolling technique. So we talked about this a bit last time, but just to sort of make sure that it's really clear, let's just say that we really couldn't deal with that very first half. So in other words, the channel that the DFE has to deal with looks something like 1 plus alpha z inverse. So that alpha is kind of the value of the post cursor. Usually in a high-speed link, that value is indeed positive, but doesn't necessarily have to be the case. So in this particular example that I've drawn here, I have actually assumed that that alpha is positive, meaning that I'm assuming my channel looks something sort of like this. Okay? So I'm still going to close the rest of the taps in that normal summer that we talked about. So I'm going to assume that I've canceled those out. But I'm basically going to try and see what can I do to deal with this very first tap. Okay? So the idea here is a lot like a carry look-ahead adder in the sense that, again, we'll just assume that we knew that the previous bit was a 1, or assume that we knew that the previous bit was a 0. Well, in either one of those cases, I could basically just statically shift the threshold of the comparator to eliminate the ISI that those two cases would have seen. Okay? So in other words, I can just have two different comparators with their thresholds shifted. And then in the digital domain, once I know what the previous bit actually was, select really what the right answer should be. In other words, which comparator I should actually be looking at. Okay? So just to sort of clarify what these diagrams here are kind of showing you, this is just saying that if you have a channel that looks like this, where the main tap is, again, just 1, and the second tap, or the post-cursor tap, is alpha, that's basically saying that there's sort of 4 possible levels that you can get, right? Because basically, even though my main thing is a plus minus 1, I'm always going to get a plus minus alpha from the previous bit, right? In other words, it's just saying that with 2 bits, there's 4 possible combinations you can get, okay? So the kind of visual mapping that you're supposed to get from this picture here is that if the previous bit was a 1, that's kind of like saying that what I'm sending this bit will be shifted up by plus alpha, right? And if the previous bit was a 0, then what I'm sending this bit will be shifted down by minus alpha, right? So in other words, it should hopefully be clear that if you just then take these two comparators, one where you've shifted the threshold up by plus alpha, then that's as if the previous bit was a 1. And if I shift it down by minus alpha, then that should be the correct slicing point if my previous bit was a 0. Okay? And by the way, of course, when I'm saying 1s and 0s, really I'm sort of assuming that differentially that means +1, -1, but hopefully that's clear to everybody by now. So does this basic idea kind of make sense to people, or? Okay, so I wanted to spend a little bit of time on sort of, what these different levels look like, because you'll sometimes actually see eye diagrams with these loop unrolled DFEs. By the way, in the communication terminology, this is sometimes called a partial response channel, meaning that you're not canceling sort of all of the response, but you're leaving some amount of intentional ISI there that you're just going to deal with later. If you look at the eye diagrams for these things, they tend to look, let's say, funny. Okay, because there's basically 4 levels in the kind of center of the point, and then there's a whole bunch of transitions that can potentially happen on the edges. So it turns out this actually has some implications on how you do the clock and data recovery as well. We'll talk about that a little bit later. This also actually turns out has some implications on how you would even adapt the equalizer. We'll also talk about that a little bit later on today. Okay? So if that basic idea makes sense, then let's see if we can actually just take it to the next step and have you guys tell me. So let's say that you're really, really pushing on the speed, and you can't even actually close the second tap. Okay, so even that one has become difficult for you to do. So in other words, now the channel that I want to deal with is something like 1 plus alpha z inverse plus beta z to the -2. Okay? So if I wanted to do a loop unrolled DFE that would deal with this kind of situation, what would that look like?
2 levels. The 2 levels?
Are there 2 levels?
I mean 2 stages.
Okay, there's 2 stages of what?
It's just like writing, take alpha z inverse out and first do the loop unrolling for the second case, second part, and then do it for the whole one.
Okay, so I think what you're saying will indeed eventually work, but I want to get really specific. I'm a circuits guy, so how many comparators do I need?
4.
Yeah, I need 4 comparators, right? Because now I have basically 4 possible data levels that I'm going to be dealing with. Right? Because in other words, now I've got 2 previous bits that could have ISI on me, right? So I have to deal with all of the combinations of those 4 possibilities. Okay? So what would the thresholds of each one of these be shifted by? So let's say this is my V in over here. What would I shift the threshold of each one of those by? And let's just walk through the list.
Alpha plus beta.
Okay, there we go. First one, you're going to shift it by alpha plus beta.
Minus alpha plus beta.
There we go. Okay, good.
Yeah.
And yes, indeed, it just keeps going, right? So you do something like, let's say, alpha minus beta, and then finally minus alpha minus beta. Right? Indeed, those are the 4 possible combinations. Okay? And so now, of course, you have to select between which one of these is actually the right one for you to look at. Okay, so now I may actually just intentionally, I'm going to just intentionally reorder things a little bit, because in order to select things the right way afterwards, if I don't draw it in the right order here, then I'll just confuse you later. So I'll just do it the way I have it actually drawn, just so that we're all on the same page. So let's say that this is plus alpha minus beta, this is minus alpha plus beta, and this is going to be minus alpha minus beta. Okay? Now you'll see why I did this in 1 second. Okay, so now how do I pick which one of these is the right answer? What sort of pieces of information do I need to know?
Minus 1's minus 2.
Yeah, so I need to know what was the previous bit and what was the bit sort of 2 clocks ago, right? So I rearranged things this way because I just wanted to sort of make my drawing a little bit easier. Right, so as an example, in this case, what I'm going to do is, based on the bit that's going to be 2 periods ago, I'm going to select between, for both of these, whether or not I choose the upper comparator or the lower comparator. So in other words, if the bit that was 2 bits ago was a 1, then I have a plus beta, I have a plus beta. Right? And then, of course, as this should hopefully be obvious, then I'm going to have yet one more multiplexer here that looks like this. And now I can actually close the loops. Right? So this one would choose the bit immediately following. And this one would, of course, choose the bit from basically 2 clocks ago. Okay? Does this kind of make sense to everybody? Or? Okay, so now obviously you can keep on doing this, but clearly your sort of complexity is going exponentially with the number of bits that you're trying to unroll. Okay? So actually, as somebody asked, I think last time, at some point, this starts looking a lot like an ADC. Because you can imagine if we have a lot of ISI, then kind of, the reference levels start looking fairly uniformly distributed. At that point, you maybe almost might as well just build an ADC and then, figure out sort of what the right answers are afterwards. Okay? So indeed, this works. And by the way, you can actually even sort of, push this one flip-flop around a little bit if you want to, as long as you don't need that information to sort of close the next tap. So in other words, you can actually pipeline this thing a little bit. But again, most practical designs, if they do any loop unrolling, they usually only do the first tap. I think only recently people started doing the second tap, but I'm not sure. I'm not really, let's say, convinced that that's actually a worthwhile endeavor because, remember, all the power that you spend for everything in front of it is proportional to the amount of capacitance you've got here in the first place. And so 4xing the number of comparators pretty quickly adds up from a power standpoint. Okay, so indeed can be done. I just wanted to sort of mention this to make sure the concept was clear. But mostly you're probably going to at most do sort of a one-tap loop unroll. Okay? Does this make sense to people? Or? Okay, so there was just a few, let's say, practical issues that I wanted to just briefly mention. This one I think we sort of mentioned a little bit last time already, but just to make sure it's sort of clear to everybody. As hopefully you saw from the homework, a lot of times you'll actually combine a linear equalizer with the DFE. And in some senses, sometimes you'll even just build the DFE just to sort of make life easier in terms of actually doing the linear equalization. Okay? So as an example, if you really have something that has, let's say, a continuous time linear equalizer, plus, let's say, the DFE, at least on, and I'll just draw it as single-ended to make my life easy, the DFE just on that very first tap, even that alone can actually be pretty useful. Okay? Because if you guys kind of remember from the homework, if we look at the actual sort of, channel pulse response, and I'll just do it, in continuous time now. So let's say that my original channel looked, I don't know, something like this, right? Approximately speaking. Well, so when I apply just the continuous time linear equalizer, keeping in mind that, when you apply linear equalization, that generally means that you have to throw away DC gain. What would the sort of, and let me, maybe draw where the sample points are here. Let's say the sample points are something like this, okay? Roughly speaking, if I just did everything with a linear equalizer, what would that new response look like? Or what would you want it to look like? And okay, maybe there's even a precursor here, but. So what should that new response look like? Just qualitatively.
The rise and fall should be sharpened.
Yeah, so the rise and fall should be sharpened, and what else?
Since you gave up DC gain, so the height will be...
Yeah, exactly. So basically, if I do just linear equalization, and let's say I do that in blue, then it should look, let's say, something kind of like that. Right? So that hopefully at the sample points, and let me do it a little bit more carefully, so that hopefully at the sample points, all of the sort of other taps except for the cursor are 0. Right? Well, okay, so now if I have even just a one-tap DFE, how should I readjust my continuous time linear equalizer? What do I want it to do now?
Leave the first post-cursor alone.
Yeah, I just want it to leave the first post-cursor alone, right? Why is that actually good? How does that help me?
It improves the amount of swing you have available to transmit.
Yeah, exactly. Basically, I'm doing less equalization, so I have to so essentially the amount of DC gain that I'm throwing away is smaller, right? So to draw it just, let's say, approximately, and this time I'll do it maybe in black, what I would now get is maybe something that sort of, just out of the linear equalizer kind of looks like this. Okay, so I still want it to be 0 at these other points, right? But now I've allowed myself to just leave some ISI there on that very first post-cursor, right? By the way, another way of saying that this allows you to give up less on the DC gain is also to say that effectively I've backed off on the bandwidth of my linear equalizer, right? Because notice, like, the width of this pulse that's coming out of the linear equalizer is roughly speaking twice as wide as it used to be before, right? Approximately. I'm not exactly 2, but ballpark. Okay. So indeed, because you always have to throw away DC gain to get a certain amount of peaking, that means you'll actually get a larger signal swing by backing off like this. Okay? So when you really do combine these two things, that means that you really do want to set things based upon sort of knowing how many DFE taps you're going to be using. You also want to build your linear equalizer actually keeping that in mind. Okay? And so I'll just mention this briefly. Turns out a lot of times people will do these DFEs not because it's actually thermal noise that's really being amplified that causes a problem, but actually just because there's a lot of crosstalk that you might be picking up at the input of the CTLE. And so if you try and do everything with a linear equalizer, you'll amplify that crosstalk. Okay? So even just from that standpoint, oftentimes you'd want to do the DFE just so that your continuous time linear equalizer won't be peaking the crosstalk, right? Which really has nothing to do with thermal noise, but for the same reason that it peaks thermal noise, it also would peak crosstalk. Okay? Does that kind of make sense to people, or? Okay, so next thing that I just want to kind of briefly mention, just to make sure people are kind of tracking, is that if you remember when I talked about kind of the oh yeah.
Just a question.
Sure.
So is the crosstalk usually on the cursor, or is it around the first tab?
You don't know, right? So you don't really know where the crosstalk is going to be. It doesn't really matter because it's not really, let's say, even if it's a parallel link or something like that, the data is independent, right? So it may indeed fall on the cursor, right? But the trick is that crosstalk usually is at a fairly high frequency, right? Because it's usually capacitively or inductively coupled, right? So just by me being able to back off on the bandwidth of the CTLE, I'll just be filtering the crosstalk more heavily, right? It's not that it's going to go away, but at least I won't be amplifying it as much as I was in the past.
Got it.
Yeah?
Does anyone sort of ever do MIMO with crosstalk?
Okay. So that's a great question. So this is, this is, let's say, one of those fun things that, whenever you take a class on this, you always say, oh, well, but, who cares about crosstalk? Like, it's just a multiple input, multiple output channel, right? Like, if I knew what that was, then I should, if the crosstalk channel is so good, why don't I just send data on the crosstalk channel, right? Okay, so that turns out it's a very, let's say, conceptually appealing idea. The only minor issue is that, again, if you think about, let's say, a backplane or even maybe something like, one of these big computer boards, this link right here may be going this way and then, crossing through some, let's say, vias or something and then going over there. This other link over there may happen to cross you for some period of time. This other link over here may cross you for some other period of time. So the problem is, generally speaking, even though you're absolutely right, I don't know all of the data everywhere on my own chip, right? I don't really have control over the entire system. So if I really had something that was purely a parallel link and I controlled that entire thing, you're absolutely right. I could really very well treat that as just some big multiple input, multiple output system. Unfortunately, practically speaking, usually you're being crosstalked on by 3 or 4 different links, all of them from completely different chips from you. But that is actually, it's a great question. If somebody figures out a way to make it work, it'll be very impressive. More questions? Or? Yeah.
So basically, here you could make the equalizer like that second, the first pole of the equalizer half of what you would otherwise.
That's right. Roughly speaking, yes.
Okay.
Now, it's not exactly factor 2 because it obviously depends on exactly the channel and things like that, but ballpark, that is indeed what it about ends up to be. And you can imagine if you cancel even more of these things, you may even be able to back off further, right? Although, for most channels, there's kind of diminishing returns after that point. But indeed, there is about that factor of 2 that it buys you in terms of the bandwidth of that linear equalizer. Okay, so unless there's more questions on this, the next thing I just wanted to sort of briefly mention is, we talked a bit about, in the context of the receive FIR filters, we talked about how sometimes you end up wanting to interleave those things. Turns out if you're operating at pretty high bit rates, sometimes you end up wanting to interleave the comparators as well, just because basically it gives you more time to either resettle the bit, or rather to make the decision, or to actually resettle the comparator after making the decision, meaning to precharge back to the sort of nominal state. Okay? So sometimes even when you do that, of course, you're still going to want to do a DFE. So you just need to kind of keep track of when you start doing these interleaving things. That's going to interact with how you're going to end up building the DFE. So the key thing to keep in mind is that, generally speaking, the settling constraint on the DFE doesn't really change. So if you start doing interleaving, at some point that you may actually be just spending more power without actually really saving yourself anything in the comparator itself. So just to kind of give you an idea of what that looks like, I just wanted to kind of quickly draw what a two-way interleaved, sometimes called DDR, just stands for double data rate, DFE design might look like, at least just for one tap. Okay? So if you did something like that, you might actually now have two independent summers. You'd have, let's say, two comparators. One, let's say, clocked off of clock. The other one, let's say, clocked off of clock bar. Okay? And then at least conceptually, when you want to do the feedback, right, you still have to scale it by some coefficient. It's just that now, since your clocks sort of look like, obviously that's clock, this is clock bar, then a lot like we talked about previously with the interleaved designs, if I need to cancel the previous bit from the thing that just made a decision, or rather, when I make a decision here, once clock bar goes high, the thing coming from clock is going to be the previous bit, right? So in other words, in order to close that loop, what you have to do is something that looks like that. Right, so in other words, the decision that came from the even or the positive clock edge gets fed back to the negative side. And the decision that came from the negative clock edge gets fed back to the positive side. And just to make sure there's no confusion, these are, of course, in principle, or at least in practice, tied to the same input voltage. Okay? Okay, so the reason I was sort of mentioning this was, again, I may have gone to this interleaving because, as an example, I wanted to relax, some of the constraints on my comparator. But notice, because I'm actually closing this first tap here, I still have the timing constraint of making the decision, going through this scaling, feeding back onto this analog node, and having it settle all before that next bit time, right? Because in this case, if I have DDR like this, each clock phase is a bit. Okay? So again, I mention this just because even though these designs are fairly common, you should really keep track of sort of what is it overall that you're building, right? And really what's going to be the sort of active constraint in terms of setting how fast different pieces of your design will really have to operate. Okay? Does this make sense to people, or?
Wait, what does this buy us again?
Okay, so in this particular example, it turns out to not buy you anything, which is kind of why I did it this way. But imagine that I wasn't closing the first tap, right? So if I didn't need to do this, then now notice my comparator. It actually has twice as much time to reset itself, right? And in principle, if I was really limited by, let's say it was a CML comparator or something like that, I've also got twice as much time that I'm staying in the input sampling phase.
Of course,
right?
not closing the first tap, meaning unrolling the first.
Okay. So now, even if you unroll it, you still have to be a little bit careful because even in the unrolled design, you still have to sort of make it both through this path, and there's this feedback path here. So this feedback path, and I think I might even be drawing this one. Oh no, I guess not. This feedback path basically would be sort of also crossing from one, like let's say from the positive side to the negative side, because that's still how it would look. But that indeed may actually be more relaxed than what you'd have to do to really physically close it. So it depends on which one of those ends up being kind of the critical path. So indeed, if you end up doing a two-way interleaved, then you should probably go ahead and do the loop unroll as well. Because if you don't, then it may not really be buying you all that much, unless just generating a clock that fast is really expensive. Does that make more sense now?
Kind of. It's still not clear that it's that much of a speed benefit, but maybe.
Well, so imagine that I wasn't doing any DFE at all, right? So if I wasn't doing any DFE at all, that's clear, right? If I'm now doing DFE, then you're right, it's not, to actually see, you have to really walk through the timing path for the loop unroll. But basically, it turns out that the delay of the comparator, as long as this forward path is not the critical one, that delay is, you're somewhat insensitive to it because basically you're going to be getting a delay from the comparator on the other way. So as long as they sort of arrive at roughly the same time, then as long as this forward path isn't the critical one, they don't really eat into this feedback path. That's kind of what it comes down to. Again, that's under the assumption that the feedback path is the critical one, not the forward one, which may or may not be the case. Other questions on this? Or? Okay, so one last just sort of practical thing, which, unfortunately, since I'm not going to be making you do layout, you won't really see. But if you ever really try and build something like this, you'll feel very, very, sharply, let's say. So if we really look at sort of how this thing is built, and I'm just again gonna, I'll draw the full differential thing just to make sure it's clear. All right, so if I look at my kind of DFE summer, all right, and let's just again even do it just with one tap, although in reality you should keep in mind I may have many more taps than that. All right, my DFE summer looks something sort of like this, right? So those are my output nodes, and of course my inputs. Okay. Now remember, you don't really know necessarily ahead of time which channel you're going to be operating on. At least not if you want to build a link that would operate or work in many, many different possible usages, right? Well, so that means that this thing down here is going to have to be programmable, okay? Not only that, if there's actually a lot of those taps, as we'll talk about in a little while, I may actually need pretty high resolution in terms of how well I control the value of that current there, okay? In fact, it may be even up to, 6 to 7 bits, maybe even more than that if you really had a very large number of taps. Okay? Well, if you think about it, that tends to mean that this DAC here is going to be pretty big, right? In particular, building a 6 or 7-bit DAC is probably way, way bigger than the transistors you're going to want to use in this thing, where you're going to want to pack everything in as tightly as you possibly can, right? Because it's your high-speed stuff, so any extra wire capacitance is just horrible, right? So if you actually look at the layout of these things, what they will tend to look like is something like the following. You may have your little, DFE, let's say the input pair. Maybe those are your switches. Maybe this is your comparator somewhere. And then your DAC will probably be, somewhere over here on the side of the chip, because you don't want it in the way of all of your high-speed, nice, clean stuff. And then you're going to have to route that wire over into here. Okay? And again, it's not that, fundamentally the DAC has to be off on the side over there. It's just you can imagine, let's say I maybe have another, DFE nearby that I want to do. If I shove the DAC right next to the DFE itself, it'll eat into your pitch, right? It'll force everything to be completely spread apart, and then you'll just be paying really big wires in the front over there. Okay? So this kind of design, even though it looks really funny, where, you have one circuit that's just physically spread in like 3 different places or whatever, it looks funny, but turns out there's usually pretty good reason for you to do something like this. Okay? The only caveat is that now you have to be really careful, because obviously there's a whole nice pile of capacitance on that quote-unquote tail node, which can cause some, let's say, interesting issues. But as long as you're careful about it, this is indeed generally how you're going to want to arrange your layouts. Okay? And this is sort of an issue, I think I may have mentioned this in the past. If you actually see a lot of, very, very high-speed types of design, this is indeed the type of thing that they'll end up doing. So in fact, for example, even this tail current source, if that ends up being big enough compared to your sort of core high-speed devices, you may even throw that out of your high-speed path and just route that tail. Okay? It does mean you're giving up some differential noise, or rather I should say common mode noise immunity. But oftentimes, if you're sort of careful about it, that may actually be, let's say, the more optimal solution just from an overall power and feasibility standpoint. Does that make sense to people? Or? Okay, great. So unless there's more questions on this, what I'd like to do is actually go ahead and move forward. And I've mentioned that we're going to need that 6 or 7 bits there. Well, it turns out the reason we're going to need that is very sort of tightly related to the fact that we actually need to adapt those coefficients. So on that standpoint, what I want to do is go ahead and move forward onto the next set of lecture notes, and now talk a little bit about how is it we're actually going to figure out what to even set these equalizers to. And obviously not from the standpoint of just straight on doing design, but given the fact that I'm going to want to try and take this link and use it in a whole bunch of different scenarios. Okay? Okay, so when we talk about sort of equalizer adaptation, the thing that you should sort of have in the back of your head, even if you haven't really looked at a lot of this stuff in detail, is there's a whole bunch of literature out there about how you build adaptive filters. And what I mean by adaptive filters is, filters where you basically tune the coefficients of those filters based on some objective function that you're interested in. Okay? So again, long list of different algorithms people have come up with to do this. So there's least mean squares, which we're going to talk a bit about today. There's something called regularized least squares. There's steepest descent. There's even things called interior point methods, which are based on sort of convex optimization. All of those things in principle can be sort of used and have actually been used in various different types of applications. Usually the differences between them have to do with sort of their convergence properties and how well they sort of obey different constraints in your system. But there's one sort of important thing to keep in mind in the standpoint of, let's say, at least this class, or at least high-speed links, which is that even though we don't really know necessarily which channel we're operating on, generally the sort of changes in channel are relatively slow. Right? In other words, it's usually like, okay, I built this link once, and then I took that chip and I plugged it in, and then it's sitting there in that same channel or same plug for, practically speaking, forever. Right? Now, okay, to be fair, even if, let's say, temperature and humidity change, that will change the channel characteristics a little bit. But point is really that generally for most of the sort of link type of environments, what you really care about is, A, will the thing just converge, period? Meaning, will I get kind of the right answer? But B, as long as it does that, I just want it to be really simple. I want it to be really low overhead, because I don't want to be paying lots of power for it. Yeah?
Do you actually care how fast this thing actually converge?
So that's kind of what I'm getting at, is that in many link usage scenarios, you may not care that much. There are some, let's say, scenarios you can come up with where you would care. Let's say, I don't know, you have some circuit switched router or something like that where you're really physically looking at different channels at different times. But in most electrical link scenarios, the convergence time is not a big criterion. Okay, and so actually because of that, that's kind of what I'm getting at, is that simplicity actually tends to be the #1 constraint. Simply because you don't want to spend a lot of power, and pretty much anything that's complicated pretty quickly ends up adding a lot of power to your system. Okay? So you should keep that in the back of your mind, because I'm not going to be talking about all of the different possible convergence sort of algorithms that are out there, but I'm really going to focus on the ones that are sort of simple enough that tend to actually be sort of reasonably well used, or reasonably often used. Okay? So the first thing I want to just briefly talk about is how you might actually adapt the continuous time linear equalizer. Because it turns out that that one was sort of, let's say, developed a little bit after how you deal with all the FIR filters. But the idea is actually quite simple. Okay? So in order to sort of motivate how you might do that, what I want to do is kind of draw a couple of, let's say, different examples. Okay? So what I'm going to be drawing here is kind of what's the spectrum of what's coming out of the linear equalizer after it's sort of gone through the channel. Okay? So as an example, let's just say that the channel response looks something like that. Okay? And let's also say that, right now, given your current settings, you set the linear equalizer to, let's say, look something like that. Okay? Just making it up, obviously. Okay? So if I did that, what would my sort of overall, and actually let me just label the blue thing so it's clear. So that's my equalizer. So what would my overall response kind of look like? What would it be? Just, you can wave with your hand or something like that. All right, so first of all, is it flat?
The equalizer.
Well, okay, so I think I drew it relatively clearly, but just to maybe make it more clear, let's say the pole of the channel is right there, and the 0 of the equalizer is right over here. So is the channel flat? No, it's not, right? So what is it going to look like? Just roughly. Yeah, I think Chintan kind of did it. So basically, obviously down here it's flat. Then you hit the pole of the channel. Then you hit the 0 of the equalizer, and then it's gonna. Actually, it'll be even faster than that because there's actually two poles there. It'll look something sort of like this. Okay. So in other words, you're not equalizing enough, right? because clearly you've still got some low-pass characteristic in that channel. Okay? So now what I want to do is sort of repeat the same situation, but actually draw it under the condition that the equalizer is properly adapted. Okay, so again, I'm just going to do sort of, some magnitude behavior. This is again going to be my channel. And then in blue again, I'm going to do the equalizer, but this time I'm going to put it in the right spot. Okay, so the equalizer will now look something, let's say, like this. There. Okay, so in other words, that's the 0 of the equalizer. And that's the pole of the equalizer. Okay? All right, so now my equalized response, of course, should basically just look flat, right? So if I do it, properly, then the magnitude, of course, will be lower than the previous case. So it should look something, let's say, like this. Okay? But now I want to sort of point out one thing. So let's say that somehow magically I could actually go and take this channel and kind of split it into two pieces. Okay? And let's say I looked at how much energy was here in sort of the lower half of the bandwidth, and how much energy was, let's say, quote-unquote, here in the upper half of the bandwidth. And you should ignore the fact that my drawing sucks and they aren't really equal in sort of length. Just assume that my labels are correct. Okay? So if I looked in the left-hand condition versus in this right-hand condition here, you should notice that they kind of look different, right? In the left-hand case, when I haven't adapted things properly, it's pretty clear that I'm going to have a lot more energy in the lower half of my bandwidth than I am going to have in the upper half of my bandwidth, right? Because in the upper half, basically, I've got that roll-off that starts happening, right? Whereas over here, when I've adapted things properly, in the lower half, I should basically have the same amount of energy as I do in the upper half, right? Now, when I say half, it's not really necessarily exactly half, because remember, I don't really put the pole at exactly the Nyquist frequency and things like that. But at least conceptually, you can think of things that way. Okay? So it turns out that one of the simplest sort of, let's say, algorithms to actually tune the continuous line linear equalizer is really just look at what's coming out of it, split the sort of frequency spectrum into two pieces, and then see if those two pieces have different amount of energy in them. Okay? If they do, that must mean your equalizer is not tuned properly. So obviously, whichever one has sort of less energy in it, you tweak the equalizer so that it has more energy in the one that used to have less, and less energy in the one that used to have more. Okay? And of course, you do that just by essentially moving the 0 and the peaking around. Okay? Does this kind of make sense to people, or? Okay, so let's see if we can actually sort of draw a block diagram of how this thing might look. Okay, so, and let me do it in a better color.
Good question.
Yeah, sure.
So why is the goal, is you said, is to make the energies in each band equal?
Yep.
And how does that denote that it's properly equalized?
Well, because notice, so let's look at this example, and maybe let me draw the thing in black more clearly so that it's easier to see. Right, so if I'm not equalized properly, right, in this region here, I'm totally flat at this level, right? But then up in the upper half of the band, I have this kind of roll-off, right? So as long as the signal that I'm transmitting is relatively white,
Okay, no, okay, see.
does that make more sense
yeah.
now?
Yeah.
Right, whereas notice here, it's flat in this band. It's also flat in that band.
No, for some reason I thought like the second half was going past the bandwidth.
Oh, yeah,
I
no,
was trying to
it
see-
shouldn't be. It should all, so
Okay,
there's a
yeah,
little
yeah.
bit of, let's say, a detail as to where exactly you set this edge over here and where you do the split point. But that's why I said conceptually think of it as splitting the bandwidth in half. There's a minor, let's say, caveat there of I think it ends up being, not exactly in half, but I think it's like 0.48 or something like that. But for all intents and purposes, just call it half.
Okay, yeah.
Yeah. Was there another question in the back, or? Okay, so let's see if we can actually sort of draw a block diagram of this thing. Okay? So you take your input, you pass it through your continuous time linear equalizer. And for now, let's assume I don't have a DFE, although you could do this with a DFE as well. I have my comparator over there. But now what I'm going to do is I actually need to look at the output of my linear equalizer. Okay? So first of all, how am I going to split this thing kind of into two halves from a frequency standpoint? What do I have to do?
It's basically an FFT engine, but just 2-point FFT.
Oh, okay. You could actually do an FFT. By the way, remember I want simple and low power. So I think I need the ADC and the FFT. So I guess you're right. A 2-point FFT is not so bad, but I think I can do it maybe with less overhead than that. But that is indeed correct. Well, there's another minor caveat, which is my signals aren't guaranteed to be periodic, but we'll ignore that too.
Can I just put a filter?
Yeah. Do I need one filter?
Two.
Two filters, right? So I basically do one low-pass filter, right? And one high-pass filter, right? Or, of course, if I've done this right, then the cutoff frequencies of both of those filters should be the same, right? There should just be some, let's say, half-point frequency, right? Okay, now once I've done that, how do I sort of decide which one has more energy? Or how do I compare the energies? Yeah, basically, I just do a peak detection, right? So I do some sort of either squaring or rectification or whatever you want to call it. I'll just draw it as sort of an absolute value here, although you should really think of that as being a rectifier or a peak detect. Okay? So then once I've got that, indeed, I know what's the energy in the lower band. I know what's the energy in the higher band. So now all I really have to do is just compare them, right? So really just subtract them off. And then since I know I want to drive that difference to 0, I'll just integrate it, right? Because I want infinite gain at DC to make it be 0. And then I take that and I just use it to control my continuous time linear equalizer. Okay? So just to be really clear, because again, remember the whole trick is you want things to be simple, right? That low-pass filter there is basically just an RC. That high-pass filter there is basically the same resistance and capacitance, just flipped over to be a high-pass filter, right? And inside of that CTLE, I'm just going to draw it single-ended, but keep in mind it's really differential. The only thing you really need to tune is actually that resistance there, right? Because by tuning that resistance, you're changing both the peaking and the 0 location. Okay? Yeah?
Is there a significant error by making that second filter high pass instead of band pass?
Oh, okay. So in reality, even this filter will end up being band pass. Although, remember, what's coming out of here actually has the low pass behavior, right? Because my CTLE already has finite bandwidth. So in other words, if I looked at the transfer function from kind of this point to this point, it would actually be band pass. Right? So kind of I'm relying on the bandwidth of the CTLE to naturally set the other half of that band pass filter. The bigger issue is, of course, these things have to kind of match, right? And you really want to set them in the right place, right? So there's a bit of an issue there. Sometimes people even close another loop that will tweak that. But, probably practically speaking, that's not super critical because probably once you've done this, if you've gotten it close to the right place, it'll give you pretty close to the right answer. Yeah?
Those filters have to be well matched to the equalizer pull.
Okay, so that is one nice thing. They don't have to match the equalizer. They just have to match the sort of bandwidth. So if you know the bit rate, then you kind of know where to put these. The bad news, of course, is if I'm changing the bit rate, then I actually have to change these along with the bit rate. So that's certainly an issue. But in terms of where exactly the channel 0 is, that you don't have to worry so much about. Because you're just shooting for something that's flat over the entire channel bandwidth. Yeah?
Does the data always have equal energy?
Okay, that's a great question. So we're going to come back to that one. In, let's say, many applications, the data has reasonably equal energy, and if it doesn't, you may force it to. But that's absolutely a great question, which is that, hey, what happens if the data doesn't actually have equal energy? Then, how the hell can you tell the difference between you having the wrong equalizer and you just having data that looks weird? Okay, so that's a great question. Keep that in mind, because I'm going to show you another implication of that and how you deal with it just using a different adaptive algorithm. But it's a great question. So in this particular algorithm, data had better be white. If it's not, you're in trouble.
that the reason why it's 0.48 or whatever? Is it for
I think
data?
that actually has to do with the fact that you don't necessarily set the equalizer bandwidth to 0.5 of the bit rate or whatever. You set it to 2/3 or somewhere in that ballpark. There's some optimization you run there. Again, I don't think it's actually super critical unless you care down to the, let's say, the last few dB or whatever it is. Yeah.
What about sort of doing this in the digital domain after the?
Okay. So you sort of, well, okay. There are versions which will turn out to do something similar, but remember, I've only got a single bit coming out of here. So I'm not exactly sure what, because in other words, if I actually see spectral differences in the bits coming out of here, that either means that my data is bad because I'm not sending white data, or it means I'm actually making mistakes. Right? Because if the data was supposed to be white that I transmitted, but the data coming out of here is not white, then that means that I'm actually making bit mistakes. And at that point, I'm hosed. I can't do anything anyways. Meaning I'm already so badly mistuned that my link is not working, and me tweaking things is not going to work.
Right. So if you have more than one port, so do you like chop it off into further?
Okay. So that's a great question. You could indeed sort of start chopping things further. You have now multiple independent, things that you have to play with. That gets pretty complicated pretty quickly. And it turns out that for most of the practical link channels, people don't tend to peak it with more than 1 0. They'll maybe do 2 zeros, and if they do, they may even fix where one of the zeros is and then just bite it if it's not exactly tuned correctly. You could indeed do that. If you really had to, I think you'd probably start using some other versions of the algorithm that basically look at certain sequences of data patterns and assume that the channel looks a particular way. I won't talk about those in detail, but if you're interested, I can show you some references on those as well. But typically, most people will sort of do a fairly simple continuous time linear equalizer. And then if they really have a fairly complicated channel, they'll deal with it either with the transmit paramphasis or with the DFE or both. And for those, I'm about to show you exactly how you can adapt to basically arbitrary channels. So that's a great question. Other questions on this? Or? Okay, cool. So if that makes sense, then actually we're going to get into sort of the heart of what most of this lecture is really going to be about, which is actually how do you build adaptive FIR filters? Okay, and so it turns out the number one most popular way to do this is with an algorithm known as LMS. In other words, LMS just stands for least mean squares. Okay, so this was really sort of developed by a guy named Bernie Woodrow at Stanford back, I think, approximately 50 years ago or so, and has really been used for kind of ubiquitously all over the place since then. Okay, so the basic idea in our context looks something like this, and I apologize, I'm again going to do a little bit of math, but I promise it's only like 3 or 4 lines. Okay, so let's say that I take my transmitted data. And by the way, right now, I'm going to, whenever I want to be talking about a vector, I'm just going to put a line over that thing just to make it clear that it's a vector. Okay? So let's say I take my transmitted data, I pass it through my channel, right? And then, of course, at the receive side, I'm going to have some noise that's being added in. And I've noted this as being a vector now because I've still got sort of a vector of transmit data coming out. Okay? And then what I'm going to do is I'm going to pass this through some equalizer, okay? Which in this case I'm just going to assume is on the receiver, but we'll come back and talk about how you do the transmitter in 1 second. Okay? So after I've done all that, and in this case I'm not, so now I'm just going to give you, I'm going to do this whole operation to sort of figure out what is the sort of analog received voltage sitting after this equalizer, okay? And at one particular sample point. Okay? So obviously as you change the sample points, then you'd fill in different values into this transmitted X over here, and that would give you different values for the final analog received voltage. Okay? So to see how we can sort of figure out how to adapt that equalizer, which the coefficients of that will just be the entries in this W vector, let's just sort of take a look at what is it that I actually receive. In other words, what is that actually comprised of? Okay? So as should hopefully be clear from the diagram, the analog voltage that I'm receiving is just something like, essentially I take my equalizer. I'm going to do a transpose just because you can think of it as just doing a convolution. Okay? I'm going to convolve that with whatever the channel did to my transmitted sequence. And that's just, of course, going to add in some noise. Okay? So just to make things clear, I'm going to call this thing over here URX. In other words, it's just like the analog voltage going into the equalizer. Okay? So this whole thing is now just going to be that W of the equalizer times URX. Okay? So just like we talked about, when we did this in MATLAB or whatever, if you want to do any kind of adaptation, what you basically have to do is figure out how wrong is what you're getting compared to what you actually wanted it to be. Right? In other words, you have to always figure out what is your sort of error signal that you can use to drive your adaptation. Okay? So in this particular case, what do you think is sort of a good error signal for you to use? What do you know you want your received thing to be? If you had an ideal channel, what would your received voltage be?
Like
Yeah.
either a 1 or a 0?
Okay, well, or to say it another, let's say to say it more mathematically, whatever I transmitted, that's what I want my received voltage to be. Right? The only caveat is, of course, there's some delay maybe in the channel. But basically, if I wanted to figure out some sort of error signal at this particular sample, I could basically say that that error signal is just essentially after the equalizer. Right? That's just a reminder, that's just XRX. My error signal is just that, minus whatever I happen to transmit at some time, and actually this isn't a vector, this is now a scalar, at some time delta samples ago. Right? Because assuming that there's some delay in this channel, there may be some, you just want to handle whatever that delay is. Okay? So that would be my error. Right? Okay, so now conceptually, what is it that we want to do to this error? What do we want to have happen to that error?
Minimizing
Go to 0.
Okay, so do you want the error itself? Okay, so you do actually want the error itself to be 0, but there's some minor detail with making the error itself 0. Let's say more mathematically, what is it that you typically will do?
Square of the error.
Yeah, you make the square of the error 0, right? Because the sign of the error is actually kind of tricky to deal with. Okay, and if you remember, we sort of said earlier that usually what you want to do is sort of, let's say, maximize the signal-to-noise ratio, which is something like minimizing the mean squared error. That's what we want to do here, too. Okay? So what we should actually really be looking at is, what is the squared error? Okay, so that's, of course, just E squared of k. Okay, now, if I just gave you, let's say a Math 101 or a Calc 1 kind of problem I said, here's some function and I want you to minimize it. What would you do?
Take the derivative.
Yeah, you take the derivative, right? So in this particular context, remember, the thing that we're tuning is the transmit equalizer coefficients. Okay? So in other words, what we're going to want to do is essentially take the derivative of E squared of k with respect to my equalizer coefficients. Okay, so just to be clear, I am taking the derivative with respect to a vector here. That just means that I'm taking the derivative with sort of respect to each one of those individual things. I've done it this way because it turns out there's a very nice sort of simple, let's say, notation for that, which is, in general, if you take the derivative of some function of, let's say, some x squared with respect to some variable, then the answer is just going to be 2 times that variable times the derivative of that variable with respect to whatever other variable it was you were taking the derivative of. Or with respect to, I should say. Okay? So this is just like, let's say, basic calc rule. Right? Okay, well, notice, what is the derivative of the error with respect to my equalizer coefficients? What is that?
URX.
Yeah, it's just URX, right? Because if I take the derivative of this with respect to the equalizer, my transmitted bits hopefully have absolutely nothing to do with my equalizer coefficients. So when I take the derivative, that just falls out, right? And all I'm left with is whatever my equalizer coefficients were in the first place. So in other words, my derivative is just going to be equal to 2e of k times u rx of k. Okay? And again, I'm using a vector here because this means that it's the derivative with respect to each one of those individual coefficients. Okay? Well, so nicely enough, this actually tells us exactly how we should create an adaptive loop. Okay? Because remember we said we take the derivative and set it equal to 0. That's basically saying that you want to take this quantity here and make it be 0. Well, so in all of the, let's say circuits and things that we've talked about, when you want to make some quantity go to 0, what do? How do you sort of tie the feedback loop around that? In an amplifier, when you want the error to be 0, what do?
Negative feedback.
Yeah, you put it in negative feedback with infinite gain at DC, which means you integrate it, right? So, for those of you guys who like math, this is just another way of saying that basically you build a loop where you just follow the gradient in terms of what should be the value of the coefficient. Okay, so to just write that out, this basically just says that, and these are usually referred to as update equations. So basically, if you know what the gradient is at one particular sample, then your new value for the equalizer should just be whatever the old value was plus wherever the gradient is pointing you. Okay? And so I'm just going to introduce one other parameter here, which is called mu. That's just kind of normalizing that step that you take. But basically, I'm just going to do that times essentially the gradient, which of course is just E of k, times urx. Okay? So that's really how you actually will build this thing. Okay? And again, this mu is just basically, it's not really arbitrary, but it's sort of arbitrary in terms of it just scales how big of a step you actually take. Okay? Does this kind of make sense to people, or? Okay, so now, by the way, if you do this, what will your equalizer coefficients converge to? What type of equalizer is this? Yeah?
DFE?
Ah, okay. So there was only two options. Unfortunately, you got the wrong one. Turns out this is actually an MMSE. Okay, and I'll actually come back in a little bit later and explain why it is. But this converges to the MMSE solution. Okay, and just kind of intuitively, this is actually kind of a good thing to notice. Notice that what I'm correlating is the error at the output over here, right, which is after the equalizer, with the input to the equalizer. Okay? That input contains the noise, right? So kind of another way of interpreting this, if you kind of think about, back in, let's say, your statistics and things like that, whenever you multiply things and average them, that's kind of like doing a correlation, right? What you're doing here is you're driving the correlation between the error and the input to the equalizer to be 0. Okay? So because that error and the input to the equalizer both contain the noise, what you're basically doing is you're including the effect of the noise. Okay? Because basically if the noise was too large, then kind of your errors would also get larger. Okay? And in particular, when they got larger, you'd also see that they were correlated with the input of your equalizer. Okay? So this does indeed actually converge to the MMSE solution. Does that kind of make sense to people, or? Igor, since you guessed the other way, is that more clear now, or? Yeah.
So I see that E of k still has xtx in it.
That's right.
So, but we don't know what that was, right?
Ah, that's true. You don't know, but let's assume that I got this right. Let's assume my equalizer is working properly and I'm making correct decisions. If I'm making the right decisions, then I do know what my own data should be, right? Now, by the way, in this particular algorithm, if I really do it this way, notice I don't actually have to know what the data is. I just have to tap off on this point and measure the correlation between that and my received analog signal, right? So I don't even actually explicitly have to know what the transmit bits were. I just have to measure the correlation between the input of the equalizer and the output of the equalizer. We'll come actually to another version, which will turn out to be the ZFE, where you'll actually have to use the data, and then you'd actually have to sort of assume that you got the right data, meaning you got the same data at the receiver as you did at the transmitter? That's a good question. Yeah.
So one confusion I have, it's the received signal is just one instance, and the sampling time, well, it's still a vector should be.
Are you talking about in this update equation?
I mean, even in the received equation.
No, so I'm writing this as one instance here, because basically, and that's actually, let's say, a good subtlety to point out, this thing here is still a vector, okay? But I am really and actually, oops, I missed one bar over there. This is also a vector here, okay? So what this is kind of saying is that, and I guess maybe to be slightly more consistent, I'll add the k onto that u over there. What this is basically saying is that you're taking the error, oh darn it, there. What you're really doing is you're taking the error that you saw on this individual sample, but you're correlating it not just with the input to the equalizer at that particular sample, but also with previous inputs into the equalizer. Right? Because if you kind of think about it, since what you're trying to do is create a filter, you need to have some information about, over time, what were the sort of errors being created by the channel. Right? So in other words, this E of k, even though it's the instantaneous value, I want to know how much of this error came from the previous bit. How much of that error came from the bit before it. How much of the error maybe even came from the bit that will follow due to precursor. Right? So in other words, when you do this adaptation here, just like when you did it in MATLAB for sort of the MMSE, you actually you do have to line up all of those vectors relative to each other to make sure that you're actually adapting the right coefficients. Okay? Does that kind of make sense? Or?
But in that case, XRX should still be a vector, right?
Okay.
So your XRX should still be a vector, right? Just enter this.
Over here. No, but so remember, because I'm doing this as a function of k, when I move to the next k, that will still just be a single sample. Right, so in other words, I'm taking the instantaneous error at this time, thanks, and I'm correlating it against all of the inputs that either are now or previously into the equalizer. Right, so maybe let's just do it with a one-tap example just to make sure it's sort of clear. Right? So let's say that my equalizer looks something like, oops. Like that. Okay? So when I do this update equation over here, I really just have one coefficient, right? The coefficient I have is basically, what is this alpha value? Okay? But in order to find that alpha value, what I really have to do is I have to correlate the current error with essentially what came into the equalizer 1 bit ago. Right? Does that make sense now? Or?
Yeah, right. I see. Well, okay.
Other questions on this? Or?
The current error is E of k.
That's right. The current error is E of k. And what came into the equalizer, so the only trick is that, you know, when I called this URX, I'm still saying it's of k here. But remember, there may be a bit shift because of this delta that I've inserted. Does that make sense? Or?
So E of k is XTX, right?
It's XTX, but there's this minus delta here.
So
And it's not actually just XTX, it's, you know, it's this whole thing is really U of k.
okay, so this is assuming you have the prior bit, or some bit.
That's right. Well, basically, it's you have the prior sample of the input into the equalizer. Right. So remember, U of k is this thing right there. Does that make sense? Or?
XTX is the correct bit.
Yeah, XTX is the correct bit, but notice I'm never really using that explicitly because I'm just really looking at what's the analog input into the equalizer. Right. So that will be the combination of what was the sort of actual thing I transmitted going through the channel with noise on it. That's what's going to show up at the input of this. So you're right, it does have XTX in it just because URX has XTX in it, but you can just think of it as being the analog input into the equalizer. Does this make sense to people, or?
So you just multiply the input and the output of the equalizer?
You're correlating the input and the output of the equalizer with, obviously, the appropriate bit shifts. Okay, so maybe just to say it another way, like when I look at this one-tap example here, right, the vector that I would be working with would just have 2 entries. Or rather, I should say, really, it'll only have 1 because there's only 1 free coefficient that I'm really tuning here, right? So that would basically say that that coefficient, which is the one that I'm tuning, I would update it by whatever that mu step size is times the current error times that vector, because I'm only able to tune that 1 coefficient. That's why I have to basically move this back by 1, right? Because I'm doing the single post cursor.
The delta depends on which tap you're adapting.
That's right. I mean, it's kind of implicit in this equation in the sense that this vector here implicitly contains time in it, right? Because if I wrote that vector out, let's say if it was too long, then this would be like my current sample and 1 sample ago. Right, and then when I shift it to the next one, again, it's current sample, 1 sample previous, and so on and so forth.
So does the delta accommodate only for the time shift in the channel, or does it compensate for the number of taps that are behind?
This delta is really compensating for the time shift of the channel.
Okay.
Right, but I guess what I'm trying to get at, and unfortunately this is a slightly bad example, in reality if I was tuning both of these, maybe it would be more clear. Right, if there was, let's say, an alpha and a beta there, right, then basically the alpha, all of these k's would line up. Right, but for the beta, when I move 1 down in the vector, that's 1 bit ago. Okay, and then again, when I go to the next sample, 1 bit down is 1 bit ago. Does that make sense? Or? Okay.
So make it clear. So tx is a vector, for example. In your case, if you assume it's a pulse, it's 0, 0, 1.
No. Okay, so that's maybe just to be totally clear. This xtx here is not a single bit.
Okay.
It's my actual data stream.
So then what is xtx k minus delta? It is the...
It's just the bit stream
and
shifted by that delta.
Okay. Right, okay.
All right, so in other words, maybe the notation is slightly confusing. What this is really just saying is, just think of this as I'm looking at this vector is just grabbing a chunk of the bit stream. And I'm just sliding which chunk of the bit stream I'm looking at, because obviously time is evolving. Right? That's kind of how that's supposed to be, let's say, looked at. Okay, so if it doesn't make sense, then don't worry, you'll be building it, so I'm sure it'll make sense by the time you do that. There are, of course, let's say, some practical issues that will come in when you really start trying to think about how to build this. And hopefully maybe these already sort of came into your mind. So the first one is that how do you really know what the error is relative to? Right? So I said that I magically sort of was going to take the error relative to that transmitted bit value. But really that's an analog number, right? And I may or may not have some hardware that tells me exactly what that analog number is to actually compare my inputs into to the equalizer against. Okay? So in other words, what this is kind of getting at is, what is your reference, or how do you even get a reference in the first place? Okay? The second issue, which is very relevant to links, is, okay, even if I find a way to get a reference, how precisely do I really know the error? In other words, can I measure it with like infinite precision? Or am I actually going to do something much more coarse than that? Right? And if I do something much more coarse, is that going to sort of screw up my whole solution? Okay? So I sort of said this another way, I'm kind of saying, how many bits of information do you actually have about each one of the error samples? In fact, how many bits of information do I even have about my analog input into the equalizer? Okay? So, as you can, well, okay, I'll get into that one second. So, first of all, the way you sort of set a reference level, or the reference level you'll generally use, is, back here when I said that I was subtracting out the transmitted analog value, what I really mean is that, and somebody actually pointed this out, if I had a perfectly good channel, then really there should be only 2 values coming into my receiver, right? There should be quote-unquote +1 and quote-unquote -1, right? Which, of course, corresponds with some analog voltage, okay? So when I say error, what I really mean is, what are the excursions, or what are the analog, let's say, voltages that I get that are not exactly just a +1 or not exactly just a -1? Right? So I've kind of, on this particular figure, I've drawn it on the upper side, but it's the same thing on the bottom side. So what I'm basically saying is my error is kind of all of this stuff around that data level. Okay? Because again, if everything was perfect, then I would just get a perfect +1 or -1. Okay? So that's sort of how, conceptually where the reference should come from. Okay? But there's, of course, another issue, which is, well, okay, fine, so I know conceptually how to find the error, but if I wanted to do exactly the sort of updates that I wrote back over here, notice these are all analog values, so I'd need, some infinite resolution ADC, or at least some high resolution ADC, to exactly implement what I wrote here. Okay? So, what do you think I'm actually going to do?
Question?
Yeah.
Can you actually, I'm just thinking, can you actually embed some pattern into your data? For example, make your average of data sinusoid or something, and feed that signal into your receiver, and
Okay.
this way you can just do the MMIC and just the same loop, LMS loop, and you just take the average, and so you do not need a high resolution ADC in this case.
I'm not sure I completely tracked what you're saying. I think you can probably do that, but I'm going to show you a way. So let me maybe see if somebody can guess. Do you think I'm really going to build a high resolution ADC? And by the way, I'll get it to work. So do you think I'm really going to build a high resolution ADC?
No.
Okay, so what am I going to do? Say that again?
1-bit ADC.
Yeah, I'm going to build a 1-bit ADC. Okay, so it turns out there's even a name for this. It's called sine LMS. Okay, so I'm actually really bad, let's say. I don't even want to deal with the analog value of the input to the equalizer. So the only thing I'm going to deal with is the sine of the analog input and the sines of the errors. Okay? So it turns out, by the way, this is called sine LMS only because normal LMS is called just normal LMS, meaning everything is analog. There are things that are called sine magnitude LMS, where one of the things that you deal with is sine, and meaning only 1 bit, and the other one is analog. There's the reverse, which is, I think, sine regressor or something like that, which means that, the other thing is analog and one of them is sine. And then finally, sine is just, the lazy man's version, which of course is what we're going to be doing here, which is just you do 1-bit estimates of everything. Okay? Because as it sort of turns out, and the real details of this are actually hard to actually prove, it turns out that because what you're really doing is correlating these things against each other, you can kind of think of it as long as the quantization error you get from doing those sign operations is uncorrelated between the two things, you're still going to get the right answer on average. Okay? Because again, as long as things are uncorrelated, then when you do this multiply and average operation, over time, you'll actually get the right answer. Okay? Does that kind of make sense to people? Or? So when you can guarantee that the quantization error is actually uncorrelated is a little bit of fun, but take my word for it, that does actually tend to work out. Okay? For, let's say, most or almost all practical channels that I've ever seen. Okay? So basically what we're actually going to do, as an example, is if we want to figure out what the error is around the high level, what we're going to do is we're just going to take a comparator, set its threshold to be at that high level, and then the output of that comparator will just give you a 1-bit estimate of the error. Okay? Similarly, if I wanted to find the error around the low level, I can again just add another comparator, where the output of that comparator would give you a 1-bit estimate of the error under that condition. Okay? So the only thing we have to be, let's say, a little bit careful about here is that right, my data, I don't know if I was transmitting a 1 or a 0 ahead of time. Right? So if I really wanted to do exactly what I wrote over here, then what I need to do is sort of figure out when I sent a 1, then I should look at the estimate from this comparator. And when I sent a 0, I should look at the estimate from that comparator. Okay? Does that kind of make sense to people? Or? Okay, now it turns out I can actually be even more lazy than this. So how can I be even more lazy than this? And by the way, just as a general rule, comparators are bad. So if you can throw one out, or two out, or as many of them out, then that's good. So can I throw any comparators out here and still get things to work?
Just one, right?
Yeah, I can actually just use one.
If it's not high, then it has to be the other one.
Okay, yeah. So basically, what you will indeed occasionally do is you'll just say, well, you know what? as long as everything is reasonably linear, there's no really extra information in the errors around here versus the errors around here, right? So what I can basically do is just throw out one of those comparators and then only do updates when I actually have valid error signals coming out of that upper comparator. Okay? Now, that's not to say that that's free, because what I'm basically doing is I'm slowing down how often I make the updates, right? Because now if I sent a 0, I have no information about whether I had an error or not. But as long as my channel changes were slow, who cares? Right? I'm willing to make that trade-off to actually get rid of the extra power and et cetera for this high-speed comparator that I would have had to build, and the capacitive loading it would have put onto me, and et cetera, et cetera. Okay? Does that make sense to people? Or? Okay, so there's now actually one other... Oh, well, I guess we'll come back to that. Well, maybe I'll ask the question, then we'll come back to this next part. So there's one other thing that I still haven't told you, though. So how in the heck did I set this threshold in the first place? How do I magically know what the data level is? Anybody have a guess?
At least you know the dynamic range of the error, and you can put in.
Well, remember, I'm doing things over a bunch of different channels. And so the loss of each channel might be different. The gain of my amplifiers or whatever in front of it might be a little bit different. So you're right, I could just find some reference voltage and just stick it there. But most likely that's not exactly going to be correct. And especially if I want to correct my coefficients to some very precise value, then I'm probably going to have problems if I do exactly that. So what else? What else can I do? Yeah.
Like we did before, like a peak detector.
Okay, that's true. You could actually do a peak detector. So I think what you're saying is do something like, take your analog input that, let's say, is, going into, well, I'll just draw it as a block here. That's feeding into your FIR. And then basically do, like, let's say, a peak detect over here. And then feed that in as the reference for that other comparator. You could indeed do that. Let's say that I want to get this right to within 100 microvolts. Tough, right? I have to build a really, really good peak detector, right? Maybe it can be done, but tends to be kind of tough, okay? And by the way, I just added some extra loading and stuff onto my high-speed signal path, which, okay, maybe is not horrible, but there's another trick you can play.
Can you just tune the first tab? Or no, not first, the main cursor.
Tune the cursor. What do you mean by that?
R is 1 plus W. Just tune W0.
Okay, so you're right. You could actually go ahead and basically tune this W0, right? But actually, I think really what you mean is, to be more precise, I think what you really mean is, why don't I just put some gain in front of here and then tune that gain, right?
Yeah.
By the way, how am I going to tune that gain? What am I going to use to tune that gain?
Same equation.
Say that again?
Same equation there.
Okay, it is actually almost that same equation, but what is that kind of getting at? If I'm really tuning it with that equation, what am I comparing my errors against?
The current bit. The current.
Okay, you can kind of say it that way. I mean, maybe just to rephrase a little bit just so it's more clear, what you're basically saying is, why don't I build a variable gain amplifier and then basically tune the gain of this amplifier until it matches a reference level out over here. Okay, you could indeed do that. Turns out, I mean, you can do it, it's not too bad, but turns out there's actually, again, I'm really lazy, okay? So I don't want to add any extra, variable stuff in my high-speed signal path. Okay, but there's a way to do something very similar to what you just said, just flipping it on its head. Okay, so in what you just said, you had a fixed reference voltage over here. And then what you basically did was you tuned that gain so that everything matched that reference voltage. What else can you do? Or how can you flip this around? I heard one person say it. So again, I have a fixed reference and a variable gain. What's the other way of doing it?
Fixed gain and variable reference.
Yeah, fixed gain, variable reference, right? So in fact, practically what people do tend to do is instead of actually, driving some variable gain loop, they just build a loop that figures out what is the data level in the first place. Okay? So I'll just quickly write what the sort of update equation for that is. By the way, this was done by Vladimir Stoyanovich, and the reference is in JSC. Basically what you say is, okay, let me just build a loop, and dlev is going to be kind of the value of that reference. Where again, as usual, since I want to drive the error to 0, I'm going to build this as an integrator, which in discrete time just means an accumulator. So in other words, what I'm going to do is I'm just going to make it so that that loop, just sort of basically like before, anytime I notice that my error is positive, then I'm basically going to move my reference up. Right? If my error is negative, I'm going to move my reference down. Now, there's just one caveat that, remember, my error updates are only valid when I actually have a 1 that I received. Okay? So to really make this work, what you actually have to do is only make this update whenever the input data bit, whenever the input data bit was actually a 1. Okay, so this I, this is called what's called an indicator function, meaning that whenever the argument to that function is true, it's a 1. If it's false, it's a 0. Okay? So in other words, what I'm basically doing is I'm now going to build something that just looks like a first order integration and just moves that reference. Yeah, question?
Now you have two MMSE loop inside the system. They actually compete with each other, and then you'd probably never converge.
Ah, I was hoping someone would say that. Yes, I do. And these are measured data that proves that I do. And by the way, I've built, 30 chips that all prove that I do. Now, the bad news is I can't mathematically prove it. The good news is nobody can. But hardware says otherwise. Okay, so you're absolutely right. I've got two loops that are completely interacting. It's really hard to prove that they actually both converge. But guess what? We even tweaked the relative time constants of the two loops about over a range of 10x compared to against each other, meaning about 100x overall. And pretty much no matter what we did, the darn thing converges. Okay? Yeah?
Is converge under all channel conditions?
So the only caveat, which we'll get into one thing in 1 second, notice that when I did this, I only had my updates when my data was actually a 1. So if I had really, really bad bit error rate and I was actually getting a lot of zeros when my data was a 1, then maybe it wouldn't converge. But kind of the good news with this is, I need to be making mistakes about half of the time to not go in the right direction. Okay, my dither might be horrible, but to really not go in the right direction is pretty tough. Okay, so I'm sure you can come up with conditions where it would not converge, but for all practical purposes, if your link was going to work, it'll converge. But those are both great questions. Okay, so I think we're actually out of time for today. We'll pick back up with this next time. So I'll see you guys next.